about a wheel. It says that a horizontal force of FAPP of magnitude 20 newtons is applied to a wheel of mass 20 kilograms and radius 0.5 meters as shown in the figure. The wheel rolls without slipping on the horizontal surface, and the acceleration of its center of mass has magnitude 0.5 meters per second. What is the rotational inertia of the wheel about the rotation axis through its center of mass? Now, the first thing we need to take into account is that, well, if there was no friction, then I would just take my FAPP, divide by the mass and get my answer, right? 20 divided, that will give me my acceleration. But clearly, my acceleration is not just applied force divided by mass of the body, right? So there is something more to it. If the acceleration was applied force divided by mass of the body, it would be 1 meters per second squared. But I find out that the mass of acceleration of the center of mass is actually 0.5 meters per second squared. What that should do is alert me to the fact that there is friction acting this way, right? And this friction is what we take into account, and we write our first equation, which is an equation of translation in a horizontal direction. So since acceleration, let's say it's this way, then F minus friction is equal to ma. Right? And once again, if it's a cylinder rotating like that, you can treat it as a circular disc, and I is equal to half mr squared. Right. So, oh, sorry, it's not a cylinder. It's I is equal to mr squared because it's a wheel with all the mass concentrated towards the side. Okay, so we have that, right? One critical equation that we know for rolling without slipping is A is equal to R times alpha. This is a must know for us to do this problem. Once we know that, let's try our torque equations. What is the torque? Since this is the center of the axis of rotation, the torque equation is F times R is equal to I alpha. The applied force contributes nothing to the torque. In fact, the torque is completely caused by the friction. Now, from this we get friction is equal to I alpha divided by R. What is alpha? It's nothing but A divided by R. So then friction comes out to be alpha I divided by R squared times A. Right? Now, we calculate I from this, which is mr squared. So this is mr. Oh, sorry. In this equation, in this problem, this is what we have to find, the moment of inertia. Okay. Now, typically you would say that, hey, listen, I can always do mr squared, but here they haven't given us that it's a uniform wheel, so we can't apply mr squared for this wheel. So forget about that. I is our unknown that we have to find. Okay. Now, plugging that back in, I get F applied minus I times A divided by R squared is equal to M times A. If you plug everything, this is, you have 20 minus I times, the acceleration is 0.5 divided by R, which is again 0.5 squared is equal to mass, which is 20 times 0.5. we get I is equal to 5 kg dot meter square. So doing a quick recap, we have a wheel and we don't know how the wheel is configured, so we cannot calculate directly what the moment of inertia for this wheel is. Now, that's our unknown. We have a wheel which is rolling that way, in that direction. There's friction acting in the opposite direction, and there's an applied force F8pp. So we write our translation equation of motion, right? And we relate that to the torque equation, from which we can find out our friction and terms of our linear acceleration. Plugging that back in the previous equation, we're able to find out the moment of inertia for the body in question, which is 5 kg meter square. Okay, and I think that's pretty much it.